nice haircut. Nice and cool for the summer. It's all right. You don't have to tell people that. Tell people you did it on purpose. Going for a new look. All right. Okay, so I think we're about halfway through the semester, right?
Sure.
Give or take.
Yeah.
So I was thinking on my drive over here of a midterm. So I think I'm going to do, we'll just do a take home. Okay? It won't be hard. It won't be hard. But I just want to test you. Well, you'll see. It won't be hard though.
When do you want to do that?
What's the Tuesday? I'll probably just put it on the webpage tomorrow, maybe. I'll let you guys know. As soon as I do, I'll let you know. And then I'll give you a week.
The exam.
Midterm. This will be a take home. Yeah. It should, hopefully it'll take you about 10 minutes. Okay.
Okay.
But anyways, you'll see. I don't want to give too much away. Okay. So last time we had gotten to the point where we were finally able to write down these Feynman rules, right? We had been dealing with, so we're interested in computing scattering amplitudes. That means we need to compute time-ordered products of operators. Time-ordered products of operators can be written in terms of functional derivatives of a generating functional, right? And then we wrote the generating functional for this interacting theory as a double exponential, right? And then we said we could expand that exponential and work out all the terms, right? But alternatively, we can work with these Feynman rules, right? And so I think leading up to this, we had computed some stuff. Yeah. So we had worked out one of those terms for phi scattering. Okay, so phi goes to phi. And we did it without Feynman rules. Okay, so we matched up the diagrams to a particular term in that expansion, right? And we wrote down what those propagators are, or what the term was. Basically, took functional derivatives, and we got down to something like this, right? And we said we can go on and on and on, and compute every term, by hand, doing it like this, right? And pulling your hair out, and that's what happened to me. Or you can go on and be smart and write down some Feynman rules, right? And so these are the well-tested Feynman rules for phi cube theory, okay? And so we said you start out, so for every process, you're given a process. So if I want, say I want to compute the decay of, well, I can't do that. Let's just do phi. So I want to compute the process of phi. How about it goes into 1 phi? Yeah, I can do that. Okay. So we want to collide 2 phi's and fuse them into 1 phi. All right. And so what we do is we start with the process and we draw external lines for each incoming and outgoing particle. Okay. And what do we do? So we leave one end open, right? That's going to be the external points. And then we join these guys using vertices, right? Remember, we only consider fully connected diagrams. Okay, so if I'm going to compute this, at leading order, it's pretty simple. There's just one vertex, right? So I would have something like this. Right? And I could go on, and there could be some higher order term that would look like this. Okay? But we'll get to this starting, well, soon. Okay? But right now, we're just focusing on tree level diagrams. Okay? External lines, connect them with vertices, right? On each incoming or outgoing line, the points coming to the vertices, you draw arrows, right? So usually incoming particles, you draw arrows coming in. Outgoing particles, you draw them going out, right? You assign momentum. So this would be K1, this could be K2. and then you use conservation of momentum to figure out all, the other ones. Right? So you write down vertices, you assign momentum, you determine any unknown momentum using conservation of momentum. And then that will, what else do you do? And then you assign these factors for the different parts, right? So any external lines, they're just one, right? They're one because we're working in momentum space, all right? Propagators. So any internal lines, like this guy, and this guy, and this guy, you assign factors of that, the minus I over k squared minus m squared minus I epsilon. Now remember, a lot of times we'll absorb that I epsilon into the m squared, but we always know that it's there. And then finally, for every vertex or every vertex, you assign a factor of Ig. Okay. Most of the time, we're going to set Zg to 1 because it's the counter term, and we'll get to it, but it'll be a few weeks. All right. But just in general, you want to put that factor there. And then for cases like this where we have a loop, you're going to have undetermined momentum, right? So you can't. So you'll have K2 here, and this is K1 plus K2. K1's coming in here. All right, so there's always going to be at least one factor or one momenta that you can't determine using conservation of momentum. All right, so if I call this L, and let me say it goes this way. All right, so the momentum coming along this guy would be what? Conserve momentum. K1 minus L, right? And then this guy would be conserve momentum. K1 plus K2, right? Minus L. Right?
Okay.
Right? Because it's got K1 minus L, and then the K2 is coming in. Right? And then what you should see is that you check, am I conserving momentum here at that point? And I am, because I have L coming in and minus L coming in. Those two cancel, and coming out I get K1 plus K2. Okay? We'll get a lot of practice for that. All right. So every loop you're going to have some unspecified momenta, and because of the form of the LSZ formula, you're going to have to integrate over it. Okay, and that's going to cause problems, and we'll start to talk about that today. For loop diagrams, you have to include the symmetry factor. Remember, tree level diagrams, the symmetry factors always cancel out, so you don't have to worry about them. And always include your counter term vertices, okay? Well, in the case where you're using loops, okay, where you have loops present, because loops are going to give you infinities, and infinities are going to cancel off with these counter terms, okay? All right? So that was the recipe, okay? And so what we did was wanted to check, this calculation that we did using matching the double exponential thing to the whatever thing, I don't remember what the other thing was, right? So we said, let's consider the case 5, 5 goes to 5, 5, right? And let's use this Feynman diagram way of doing it, right? And using our Feynman rules, we assign momenta, we conserve momenta at the vertices, and we wrote down the amplitudes, right? And you can break it down, and I still do this to this day. There's no fancy schmancy way of doing it. Just write down the factors, because you always want to make sure that you can cancel off all the factors by and all that stuff, right? So they got 2 factors for the vertices. You got 4 external legs, right? And then the 3 propagators corresponding to the 3 diagrams, all right? And that's it, all right? That's it. That's the amplitude. You go back and check the way we did it before. That's the same exact answer, but I just did it in 30 seconds. Right. The hard part is when you take that amplitude, you square it. Okay. There's no getting around that part. Okay. So we wrote down the T matrix. So remember, the S matrix we found it breaks down into some factor of 2 pi to the 4th, some energy momentum conserving delta function, and then whatever's left over. And whatever is left over is called the T matrix. Right, so we strip that off, and that's what we compute. Okay. Sometimes you'll see it called T. Sometimes you'll see it written as kind of a script M. think Peskin uses M. Okay, so if you ever look in the Peskin book, M is what we call T. Okay. All right, so we wrote down the amplitude, and we said, you can do some simplifications and introduce these invariants that are called the Mandelstam invariants, and they're just basically, squares of sums of the external momenta, right? So you have an S parameter that's typically related to the center of mass energy, and then T and U variables that depend on, the way you define the momentum. Okay. And these guys always obey a nice little relationship. S plus T plus U is equal to the sum of external masses. Okay. You can always check that. Now, S plus T plus U is only good for 2 to 2 scattering. Okay. If you go to 2 to 3 or even higher, you're going to have more invariants. You're not only going to have 3. Okay. That's a common misconception. Okay. But whatever those invariants are, the sum of them will always give you the sum of the external masses. Okay.
You say these 3 neurons today, 2 to 2.
Mm-hmm. Yeah. Right.
Yeah, different for 2 to 3.
Yeah, 2 to 3 because you have oh crap, you're gonna make me count. But you can sum. There's more. So we here in our ST and U we summed K1 with K2, and then here we took K1 with K3, and then here we took K1 with K4. Right? We took all the different combinations, and we get 3 invariants. But with more legs, you're going to get more combinations, more possibilities. So it's going to give you different invariants. Okay, we like to call those the Jackson invariants. Just kidding. They don't have a name. We can call them Jackson invariants if you want. Okay, so we have the scattering matrix, and then I skipped over all this crap because it's just kinematics. Okay, just working out the kinematics, and the only complication is that we're working in Minkowski space. All right, but it should be stuff that you guys should be able to do. Okay. So there's, working out the kinematics, and then I talked about how you get to, compute a cross section, and we went through these arguments in quantum. So I skipped through them. The only complication is, working in 4-dimensional space, but you can follow this stuff. The important part is, I'm getting to it here, equation 58, right? So this is the differential cross-section. Remember in quantum when we talked about scattering, we were always interested in computing the differential cross-section. Okay, so this is what it looks like in quantum field theory for a 2 to 2 process. Okay, so it's in the center mass frame. You can always boost to the lab frame, but typically we'll work in the center mass frame. We're theorists, so we're not going to worry about whatever the lab frame is. Okay. You're theorists as soon as you walk through this door. Did you guys know that? Okay. All right. So you see that it goes like the matrix element squared. That thing, the T is basically a matrix, okay? Just like we learned about in quantum. So it's the matrix element squared. You got some constant factors out there, the 64 pi squared, the S, the Mandelstam S, which is related to the center of mass energy. Right? So that's a constant. Okay. And then you've got this ratio of the magnitude of the 3 momenta for the outgoing particle and the incoming particle. Okay, and those I derived, expressions for in terms of the Mandelstam invariance. All right. Okay. So then we talked about the total cross section. Sometimes if you have identical particles in the state, like you would in our case for phi goes to phi, you can't tell those 2 particles apart, right? So you have to include a symmetry factor, right? And so you had to divide by whatever the symmetry factor is, and in our case it was 2. Okay. What is this? So yeah, and you can always go back and forth. It's just a matter of taste. If you want to work with S and theta or S and T, right? You can write down a relationship between T and the scattering angle. It's the same scattering angle we talked about in quantum. Okay, It's just what you want to work with. Sometimes it's more convenient to work with S and T, the angular part. But sometimes you want to, the angular part is more physical. You can, because you understand what that is. All right. So that's what we did last time. I think is that where I stopped? That's where I stopped, right?
I think so.
Okay. Can somebody help me see which one it is? Well, let me just do this because I can't. I've got so many. Okay. Hold on, I got a technical delay here. So is there you guys have questions about that stuff? I mean, it's pretty straightforward, right? Using the Feynman diagrams. Don't laugh. It's pretty straightforward, right? You agree, right?
Yeah.
I mean, you write down the diagrams. You use the rules. All right. Okay. All right. So before we go forward, we need to talk about. We're going to have a little. What's it called? A little excursion here, right? Away from our discussion, and talk about what we call God-given units or natural units. What happened to mine? Okay, here it comes. Okay, because it's going to be an important part of what we're going to do. So we're moving, so we've done pretty much everything you can do for tree level. Okay, in this theory, we've computed the one process of, importance. The phi goes to phi. You can go higher in external legs, right? But that's about it. We know how to compute a cross section. That's all you want to do. So what we're going to do now is just start to talk about how to compute these higher order corrections, right? Because they're going to become important, right? We compute these things in perturbation theory, right? And so when we only include tree level diagrams, we're missing a lot of stuff, okay? And sometimes that stuff doesn't really make a big difference. Most of the time it does, okay? So we need to talk about that. And I need to introduce some language, not some bad language, okay? Because your sister's here, I'll try not to use any bad language, okay? So, like I said, the first day of class in here, those constants, which I won't even say their names, were dead to us, right? We set them all to 1, okay? And when we do that, the units, some people get tripped up on the units. Like the units seem weird, right? So I thought I'd put together just a few slides and just discuss these units, okay? So the nice thing about when you do this, when you set all these constants to 1, is that everything has units of energy now. It's either units of energy or units of inverse energy, okay? So for example, you can write down time. Time would be what? If you set C equals to 1, let me think how to. So I always do this. How do I do it? Let me think. If I set each bar to 1. Okay, so here, I want to work in reverse. Okay, so mass has units of. Well, no.
Yeah.
Yeah, it has units of kilograms, but this isn't freshman physics.
Inverse of energy.
So mass, so think of it this way. E equals mc squared. If I set C equals to 1, what units does mass have? Energy, right? So mass has units of energy, right? That means that lengths have units of what?
Inverse of.
Right, inverse. So 1 over energy, right? Time has units of?
Inverse of.
Right, inverse of energy.
Right.
Okay? And I don't know, I'll let you condensed matter people work out what some of those other things are, okay?
Yeah,
That have to do with it. All right, so everything can be written in terms of, everything has dimensions of energy, okay, or mass, okay? We go back and forth. High energy theorists talk about mass, talk about energy in the same sentence, you know, the same thing to us. Oh my God, it's
Sorry.
Why would you find length as this equation?
That's what I'm trying to, I was trying to recall that. I don't know. Let me come back. I'll have to come back to that. I'm not sure where that comes from.
What, it's good equation 2? It's length over length per time.
No, three.
No, three. Three is the one that's.
It seems to be part of the constant difference in the wavelengths.
It could be. Yeah, you're probably right. I'm not sure.
But it multiplies on 1 minus cosine theta.
Well, the 1 minus cosine theta wouldn't change the units. Yeah. So yeah, you're probably right. Okay, so a lot of times what we're going to be interested in is what we call the mass dimension or the energy dimension of an object. Okay, so like when we write down our Lagrangian, you know, we'll have some term that goes like the mass squared times phi squared. Right? And we'll be interested in what's the mass dimension or what's the energy dimension of that term, right? And what we do is we usually, to denote that, we'll put it in square brackets, okay? So we would say, you know, the mass dimension of the Lagrangian for this term, it would be like that, okay? All right, some things are easy to figure out what the mass dimension is. Some are a little more difficult, okay? All right, and when we take the mass dimension, some objects might have negative mass dimension, okay? And we'll see an example of that, okay? Or even zero. It might not have any any units of energy or mass, okay? So let's just see how this works by example, okay? So for example, the mass dimension of mass is 1, right? It has units of energy, right? So that it has mass dimension 1. Is this making sense? It's just counting the factors of energy,
I think so.
units of energy.
So like m squared.
Yeah. What would m cubed be?
Yeah, 30.
Okay. What about a 4 vector, x mu? I mean, you can see the answer that it's -1, but why is it -1? What is a 4 vector? What's a 4 vector made of?
The
3 vector and a time component, right? And we saw both of those have units of inverse energy in our natural units, okay? So that's why that 4 vector has a mass dimension of -1. What about the derivative? 4 derivative? It goes like d by dx, right? So if x has units of inverse energy, then d by dx must have inverse of inverse, which is +1. Okay? And then finally, like an integral element, let's say there's d factors of it. Okay? It goes like, so it would be d dx. Right? And we know that x has units of
inverse.
inverse -1. So if we have d factors of that, we would have minus d. So it's additive. Okay? All right? That make sense?
Okay.
Okay. All right. So and that last term obviously is kind of a spoiler alert that we're going to be working in d dimensions. Okay, not necessarily 4 dimensions. Okay, so what about a Lagrangian? Okay, what about a Lagrangian where we include all vertices? Okay, so see what I'm doing? So I have the normal free Lagrangian, right? And then I'm adding every vertex I can from n equals 3 up to some big N. All right, and then we want to work out what the mass dimension is. Well, how do we do that? Well, we can start with the action. All right, the action's defined as, in our four-dimensional or d-dimensional way of thinking, it's an integral of the Lagrangian, right? That's what the action is. Okay, so how can I use that information? And well, we know that the generating functional is all that crap. Okay, but what do we know? We know that the action has no units, right? Look up there at the definition of our generating functional. Can't have units, right? Because it's exponential of s. Okay, so it can't have units. It has to be dimensionless. All right, so if s is dimensionless, let's try to see if we can use that to work, kind of deconstruct our way back and work out what some of these terms are in the Lagrangian. Okay, so the Lagrangian, or if the action is made up of the integral element and the Lagrangian. All right, so we can split those two up. All right, so the mass dimension is the mass dimension of AB. Like I said, it's additive. Is the mass dimension of A plus the mass dimension of B. Okay? So that's how I got to the equation above, equation 12. Okay? And so what that tells us is we know that this guy is minus D. Right? So the Lagrangian has to have units of D, the number of dimensions. So if we're in 4 dimensions, the Lagrangian has units of 4. Okay? Mass dimension of 4.
Density of height.
Hmm?
It's actually density of the.
Yeah, but like I said, in this class, that thing is the Lagrangian for us. Yeah, classically, it's the Lagrangian density. We just call it the Lagrangian. Yeah. I have to not say density a lot. Okay. All right, so we know the Lagrangian has mass dimension of D. All right, so we can use that to figure out what the mass dimension of the field is. Right. So I can look at that mass term, which goes like mass squared phi squared, right? And it's additive, so it's mass squared plus phi squared, right? And that's equal to the mass dimension of the Lagrangian, which is D, right? This guy has 2 units of mass or energy, right? So it gives us a 2, and this guy is also going to give us another factor of 2 out in front of the mass dimension of phi. Right, so we can solve for the mass dimension of phi in terms of, what is that moving? What was that? Can you see my mouse on there? Oh, it vanishes.
Weird.
All right. Oh, you don't say. Okay.
It's the same round.
All right. It's slow. Okay. Come on. Okay. Oops. Skipped ahead of me. All right, so we were right here. Okay, so I can use that to solve for the mass dimension of the field, and I find that it goes like that: d minus 2 divided by 2. Okay. So in 4 dimensions, it's what? 1. Right. So the scalar field has a mass dimension of 1. All right. Another thing we'll be highly interested in, are the mass dimensions of couplings, because that's going to tell us a lot about the behavior of the theory as we go to higher orders in perturbation theory. Okay, we'll see why later. Okay, but let's look at that vertex term. And remember, I'm including all the vertices from 3 up. Okay, so again, I've got the mass dimension of the term. I can split it into the mass dimension of the coupling. There's the n factors of the mass dimension of the field. Right, and I solve for the mass dimension of the coupling, and I get this expression. Okay, and in particular, if I put in n equals 3 for the phi cubed vertex, right, I get something that looks like this. Okay? And you see that if I choose d equals 4, this guy's going to have mass dimensions, right? Mass dimension of 1, right? However, if I choose 6, if I work in 6 dimensions, this guy is dimensionless. And it turns out that dimensionless couplings is a very, very desirable quality in a theory, okay? Because it's going to tell you whether or not, right off the bat, you can look at that, you look at a theory and say, uh-oh, I'm in for some trouble, okay? And we'll see why, all right? But I just wanted to show you guys how we, can compute the mass dimension of an object, what a mass dimension means, because we'll use that terminology, okay? All right, so from now on, until I say so or say differently, we're going to be working in 6 dimensions. And, okay, let me see. This is R. So that brings us to the wonderful world of radiative corrections. This is a big moment in your life. I'm just kidding. No, this is the point where we start to calculate how we figure out how to calculate these loop diagrams. Okay? And so if I think about loops, I automatically think about Fruit Loops. So that's my homage to Fruit Loops. All right? And it's frozen again. Awesome. Okay. Oh, Chrome. That works. All my toolbars are gone. Technology. It's a good thing Austin's sister's here. I'll be dropping some form letter words right now. Okay. I'll tell you what. Let me just close. Give me just a second here. Come here. I can't even. Too many tabs. I hate having too many tabs open. I start feeling claustrophobic. Nope. Mm-hmm. Now that's the way I like it. All right. Okay. All right. So we've computed everything we can compute to lowest order. All right. There's not that much in 5 cube theory. All right. We just basically computed 2 to 2. And like I said, you can go on and compute higher, numbers of legs. Right. Compute like 2 phi scattering into 4 phi, and so on and so forth. Right. But what we want to do is move on to higher order corrections. Okay. The reason is, you may be asking yourself, why do we, even worry about those terms if we're just, computing things to leading order, right? But the problem is that a lot of times in the real world, if we truncate this series, and that's what we're doing. Bless you. That's what we're doing when we cut off when we just consider this diagram, we're truncating all, the perturbative series, okay? And for whatever reasons that we'll get into, I'll explain, you're going to encounter large uncertainties, okay? So you could compute that thing, and then you would compare it to experiment, and you could vary the variation of the parameters is going to cause a big uncertainty in your theoretical prediction. Okay, so what you have to do, and that's basically just due to the fact that we've cut this series off, right? So the idea is that as we go higher and higher orders in this perturbative series, our predictions will get better, right? Because if I could compute this to all orders, I'd get the exact answer, right? But there's always going to be a leftover uncertainty, just because we're cutting off the series. Okay, so the name of the game is to compute, until you can get within experimental uncertainties, basically. Right? And then you can blame them for not being precise enough. Okay. So a lot of times you'll have, if you're considering, so this was my thesis project. I was considering top quark pair production with Higgs bosons. Okay. So you see these are quarks annihilating through a gluon into a TT bar pair, and the Higgs coming off one of the top quarks. It doesn't matter. But so you can compute this process, and leading order will give you a number, right? But it turned out that the uncertainty was too large. Okay, so we had to go the next to leading order. So what we call next to leading order, NLO, right? And at NLO, at next to leading order, so we're going higher orders in the couplings, okay? Right, the couplings, so the QCD couplings, right? And there's no, so this goes like G squared, right? There's no G cubed correction, so you have to go to the G fourth correction. Right? But there's different contributions, so you have loop diagrams, which we're getting ready to talk about, but you also have diagrams like this. Right, where this is a diagram where you don't have a loop, but you have this particle that's being shot, that's being emitted out here, right? But the idea is that sometimes these particles are emitted in the same direction as this guy, and so they might get missed, right? And they come in at the same order as the loop diagrams, okay? So that's why we have to include not only loop diagrams, but what we call real corrections. Right? And we'll get to those. We'll talk about those and why we have to do that. All right. Yeah. Okay. All right. But let's start with not TT bar Higgs, but the simplest thing that we can think of, and that will be loop corrections to what we call the propagator, right? The 2-point function. Okay. What do I want to do? All right. So what we remember we talk about the exact propagator, right? The exact propagator meaning keeping all terms, right, in the perturbative expansion, right? And that would diagrammatically it would look something like this, right? You can separate it to terms like this, where these blobs are basically all orders of loop corrections, okay? And there's going to be a perturbative series in the blobs, right? But we know in the non-interacting theory and free field theory what the propagator looks like. We computed it a couple weeks ago, and it looks just like that, okay, in momentum space. All right, and what we want to do is to derive, in a what do I want to say? In a sophisticated way, an extension of this or the generalization of this for interacting fields. Okay, and when you do that, the form of the propagator that we'll compute is called the Lehman-Kaler. I think it's Kaler, not Kalin, but I think I'll have to look it up. I know it's Lehman, but I'm pretty sure it's not. I don't think it's Lehman-Kalin. I think it's Lehman-Kalin. Anyways, doesn't matter. The name of the propagator is going to be. We want to get it in the same form. Okay. All right. So I'm just going to warn you. The next, I don't know how many slides are probably going to be the most painful slides of your life. All right. Okay. So let's start by working out the exact propagator. Okay. In terms of fields, we know how to write it down. Right. It's a time ordered product of two fields. Okay. we want the LSZ formula to be valid, so we're assuming that the VEV is 0 and the single particle states have the correct normalization. All right, but like we've seen, it's going to be to our advantage. I guess we haven't seen it. I've told you, but you're going to see that it's to our advantage to move away from 4 dimensions, right? And it's for 2 reasons. One I've already mentioned, which is when we work with phi cube theory in 6 dimensions, it allows us to have a nice discussion of basically the whole spectrum of quantum field theory, okay, with a well-behaved theory, right? So we can talk about renormalization and real corrections, and go on and on and on. Talk about beta functions and all the stuff you hear about in quantum field theory. We can do it in a simple toy theory or simple playground, right? And then next semester we'll get into real world stuff and complicate our lives a lot. Okay, but anyway, so that's one reason. The other reason is to compute these loops. You have several different choices of how you compute these guys. They're obviously difficult to compute. You can't just integrate over them simply. So there's different techniques, and one of these techniques is called dimensional regularization. Okay. So that's going to take us we won't be working in 6 dimensions there. We'll be working in D dimensions, D less than 6, okay? And then we'll take a limit to where like I said, we'll get there, okay? But these are just the reasons we're working in extra dimensions. You guys know who that is?
That's awesome.
Yeah, okay.
Obviously.
I didn't know if you don't know.
Oh,
Never watched The Twilight Zone?
Zone?
Have you heard of The Twilight Zone? Okay, you should watch The Twilight Zone. It's good. But he always talked about...
You are intrigued about the dimension.
Yeah,
the dimension not only of size and sound of mind.
Right. So yeah. Okay. So let's see how this stuff works out in D dimensions. Okay. So first, I'm going to show you how we kind of generalize our normal 4-dimensional stuff. Right. So single particle states have the normalization. So I'm just listing this stuff out. Right. So instead of a factor of 2 pi cubed, right, 2 omega, blah, 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 you insert d minus 1. Okay, so if we're working in 6 dimensions, that's going to be 2 pi to the 5th, and that's going to be a 5-dimensional delta function. Okay, and you can go on from there. Omega is still omega, right? We don't do anything to 4 vectors, okay, external 4 vectors. Those stay the same. So, invariants are invariants, okay? The completeness relation becomes a little more complicated. So remember, this is a D3 integral. It's the integral over the spatial, or the corresponding momentum part, right? This is the D ellipse thing that Shunicki writes down. But we can generalize that to D dimensions. It just looks like that. Right, and then finally, the propagator in D dimensions, you just generalize it from 4 to D, and it just looks like that. Okay, so let's get into some stuff here. All right, so we want to, like I said, we want to compute the interacting theory exact propagator. All right, and so let's do this when we write down the 2-point operator, right, we're taking the time ordered product. Right? So that means we have to consider both cases. So in this case, we have to consider, the time x is before time y, and then vice versa. Okay. But for the next few slides, let's just focus on one particular case. Let's say we know that x0 happens later, whatever. Okay. All right. So let's take this guy. So that's why I'm getting rid of the t operator there. Okay. All right, so we have a multi-particle state. Okay, so we want to try to split this up. So what we can do is we can insert a complete set of states. Right? But what does a complete set of states look like for a multi-particle state? That's the question, right? And to see, we can plot the energy. Okay, so the energy of a single particle state is pretty simple, right? It looks like it's just a line, right? So it's at lowest momentum, zero momentum, right? The energy is just due to the rest mass, right? And then the energy goes like p squared, right? So we would have something, parabolic, okay? For a multi-particle state, you have, again, at zero momentum, you have 2 rest mass, right? 2m. And you have the case where, say, one particle is still and the other particle is moving, right? That moves along the line. But if both particles are moving, that whole band fills up, right? There's a whole band of possibilities of energies, okay? So we have to take that into account when we write down our complete set of states, okay? So we're not inserting, so if you go back and look, when we insert these complete sets of states, we have to include, that behavior, okay? All right, so we were assuming that we have a unique state with zero energy and zero momentum, and we're going to call that the vacuum. So we have a vacuum state, and then we have the higher order state. So we have the single particle state, and then the 2 particle state, which is that mess, okay? All right, so we have the single particle state, has minimum energy of equals m. The energy goes like p squared plus m squared, right? And this is just all saying what I just said. Why did I put this slide in here? I don't know. Okay. All right, so we have basically, like I said, 3 states. The ground state, single particle state that we denote by K, and then we have multi-particle states. And so I'm going to consider more than 2 particles, and I'll label the number of particles by n. Okay? So when we sum over the complete set of states, we're going to have to include all these states. All right? So in other words, here it is. So I'm taking my 2-point function, and I'm inserting a complete set of states. Okay? First, the top line, I have the vacuum state. Okay, that's pretty understandable, right? Next, I have the single particle state. That's pretty understandable. It's just the integral. Here's the outer product operator that you associate with the insertion of the completeness relation. And you're integrating over the momentum. Okay? The next case, again, it's pretty straightforward, but these are multi-particle states, which we still don't really have an idea of how to work with. Right? But we know that you still have to integrate over the momentum, and you got to sum over all the particles. Okay? I told you this is going to be painful, so don't say I didn't warn you. All right? Yeah, and the sum over n, I'm being a little sloppy. It's really schematic because there's a lot of parameters and things going on. Okay, but let's just imagine that we can do this. Okay. All right. So what's that top line? It's the product of 2 what? Yeah, it's a product of 2 1-point functions, right? So that's what gives us this term. Okay, so that term just reduces to a product of 2 EIKs. Right? One is x, and the other is y. Y is 1. I'm not sure why 1 is.
Some squared into ID. Theory.
Yeah, I don't know why 1 is plus and 1 is minus. I'll have to think about that. What about the second line? What is that? No, I had this backwards, right? The first line, the top line, is what? Those are VEBs.
Right.
And the VEBs we've set to 0.
Okay.
Right, so the VEBs give us 0. It's the second line that are the single particle states, right? And those are the ones that give us this. So that's why, because this guy, the K is in the bra, over here the K is in the ket, that's why they differ in sign. Okay? Yeah. All right? Because 1 is, yeah, exactly. Okay, sorry. You're kind of zoned out there for a minute. All right? So we've got those 2 terms worked out. One's a nice little exponential, and the other one just completely goes away. Okay? And what we want to do now is try to simplify the second term. Okay, and to do that, I want to rewrite, I'm going to do a little trick where I'm going to rewrite this field in the Heisenberg picture. Right? Remember the Heisenberg picture, these are operators. No, I'm sorry, I'm rewriting it in terms of the Schrodinger picture, right? So I'm rewriting this guy as I'm sandwiching it between two translational operators, right? And this guy doesn't depend on the space-time dimension. Okay, so this is just a four-dimensional a really d-dimensional generalization of what we usually do, all right? So if I plug that in for one of those terms, okay, what happens? Well, the exponential on the left hits a vacuum state, right? Vacuum state has 0 4 momentum, or 0 of 3 momentum. So that gives you an e to the 0, which is just 1, right? The other guy, when it hits that, gives me e to the ikx. Okay? E to the ikx can come out, and I'm left with this thing. So it looks almost like a single particle, one of the single particle states. Right? And likewise, for the other term, I can do the same thing, and I get a factor of e to the minus iky. Okay? So when I plug it back in, though, I've got an overall exponential, and now I've got something that looks like modulus squared. Right? Because the first one gave me 0 kn, and this one gave me kn 0. Right? So it's like the modulus squared of that matrix element, whatever that matrix element is. Okay? Let's take a break, and I'll pick up right here, okay? Just a couple minute break, catch our breaths. All right, so let's try to regroup here and figure out what the hell we're doing. Okay, so what we're interested in is trying to come up with a way to write down an exact propagator in an interacting field theory, right? And in a free field theory, it's pretty simple, right? It just takes that 1 over k squared minus m squared form. But now we're trying to figure out what it looks like in a full interacting theory, okay? And so what we did was we started with the expression for the propagator in terms of the fields, right? It's this time ordered product of two operators, the two field operators. All right, we're moving into d dimensions, okay? We notice, we ask ourselves what states are there, right? We want to be able to, use our normal trick, which would be to insert a complete set of states to separate those operators, right? And break them into one particle states, okay? And so what we ask ourselves is, what are we summing over, right? And so we said, well, we'll have to sum over the vacuum, we'll have to sum over the single particle state, and then we'll have to sum over these multi-particle states, okay? Because they're all going to be present, right? So that's what we did, right? So we included those states and we inserted them in between our two operators, okay? And so that the top line was the vacuum, and the second line the single particle, third line multi-particle, okay? The top line we recognize as 0 because we're assuming the VEV is 0, okay? The second line we recognize as some combination of single particle states, and then that multi-particle state we still don't know what to do with, but we can use a trick and rewrite the field in terms of the Schrodinger picture field, right? And then use our knowledge of these momenta states to compute those exponential operators, right? And when we put it all back together, we got down to something that looks manageable, right? We've got this thing from the single particle states, we've got this thing, and then some matrix element squared, okay? So it's starting to look manageable, right? But we still don't know what that garbage is, okay? But what we can do is we can kind of sweep it under the rug because we know that it's coming from, remember, the two particle states are coming from that band of stuff, right? And so typically what you do is you kind of sweep it under the rug, not sweep it under the rug, but just rename it, right? So you group this stuff together, which is just, what it is, right? So you introduce a delta function that's telling you that you have to be above, basically, the delta function is ensuring that you're above that two particle line. So you're above this guy. Okay, so here, that big M squared, I think I'm taking this from two different sources, but where am I? Shit. This big M squared here would be 4, so this is like the total mass, right? So M is equal to 2M, right? So M squared here would be 4M squared, 4 little m squared. Okay, so that's how, so what I'm saying is that we're using the Mandelstam invariant, right, instead of momenta, but that guy is this colored band, okay? That's the contribution from that. So that stuff we can describe as a density, right, a density functional, okay? And if I do that, I can rewrite things in a little more compact way. Right? I don't have that matrix element squared, sitting around. It's kind of sandwiched into this spectral density function, is what they call it. But anyway, so we've separated it into something that looks like, a single particle state, and then this multi-particle state, which has a single particle factor in it times this density functional, whatever spectral thing. Okay. So what do we want to do? Well, first we have to consider the fact that we've only computed part of the time ordered product. We only did the first part, right? But if we go back and do the second part where y happens later, then we would get the same thing. We just need to flip x and y. Okay, so we should see some difference in signs in these exponentials because we're flipping x and y to get that term. All right, so the total term, we have to put it together, Okay, we put it together. We include some Heaviside functions, right, that denote that this is, when x naught is greater than y naught, and this is when y naught is greater than x naught, right? And we can write down what the solution looks like, so we can group together the non-spectral density function parts, right, the simpler single particle part, along with the second term, which is all that other mess. Square brackets, let me remind myself. The term in the square brackets. Oh, right. The term in the first square brackets. This guy, if you go back and check your notes, which I'm sure you guys do on a regular basis, you'll find that this is nothing but what we call the Feynman propagator. Right? That's back when we first encountered the Feynman propagator for field theory. So that first term is just the Feynman propagator. Right? So the corrections are coming from that second line. Right, and so let's see. The only thing we mentioned was that in the second term, wait, K naught is equal to S. Let me try to remind myself. So K naught, because S, okay, so S, integrating over S is like integrating over energy, and integrating over energy is like integrating over K naught, right? Because K naught's the energy component of the 4 vector. So let me see if I can make sense of this statement that I wrote. In the second term, K naught is equal to S. K naught is equal to S. So, I'm saying, Oh, I think what I'm saying is that okay, so I think I understand what it is. So I think what I'm saying is that when we computed this Feynman propagator, we didn't. So when we computed that guy, we took K naught to be M, right? I think. I'm trying to remind myself. I don't remember, but I think what I'm doing here is that this second term here, it looks a lot like this guy. The only difference is what the K's are, right? So I think I'm taking K naught, using K naught is equal to S, or K naught squared is equal to S, rather than K naught squared is equal to M squared, right? So what you see is that I get something that's propagator-like, right? But I have S instead of M squared. Okay? Okay, I'll have to go back and look at my notes, try to remember exactly what I'm doing there. Okay? But we end up with something that looks like this. So we can factor out the single particle thing. We have the bare, the non-interacting propagator, and then we have terms from the propagator. Okay? And that stuff in the square brackets is exact, right? It's exact. We didn't make any approximations. We didn't chop off, any parts of the computation or anything. So this is exact, okay? So this is exactly what we wanted, which is a generalization of that the non-interacting propagator, okay? So the full exact momentum space propagator is going to be this part that we're used to, plus this thing, okay? And having gone through this, I can tell you that we will never use this, okay? But it's good to see one time, okay? If you're interested in quantum field theory, because you will see, when you look in books, you'll see stuff like this, right? You'll see mentions of the spectral density function and all this stuff, okay? So it's good to see, one time.
What is rho S?
Rho of S is that density. It tells you where the state,
Oh, the bands.
yeah, it's the density function, the spectral, they call it the spectral density. I don't know what the spectral part of it means, but it's just basically a density, density. Okay. All right. But like I said, you'll have to do something on the midterm with the Lehman-Kalin propagator, but after that, you can forget about it. Okay. So this is what you asked me what the spectral density function is. It actually includes some single particle states, some bound states, and then the two particle states where you have this continuous hump. Okay. And what would we have for the single particles? For the single particle theory, this stuff wouldn't be here, right? Or non-interacting theory, we would just have this one pole, like k equals m, k squared equals m squared, right? Yeah. So the quantity m in the exact mass. So if you go back and you look at this guy, right? What we're going to see is that this guy here, the mass parameter, doesn't necessarily correspond to the mass parameter that we write down in the Lagrangian. Okay, the 2-point function, when we compute the higher order corrections, are going to make corrections to that parameter. Okay, and so what we'll actually compute. So when we compute and we'll get an expression for this mass squared parameter. That's the actual physical mass. Okay, or it's as close as we can get to the actual physical mass, right? Because we'll compute out to some order, and then at some point it's just going to get too hard. We'll have to chop it off. Okay.
The diagram is 2n. Yeah.
Mm-hmm.
The physical mass is n squared, 2n squared.
That is the 2m squared. Is the what do you? I'm not sure.
This n is the one that's using the Lagrangian.
I want to say the m there, the little m there. I want to say yes. Is what we would call the bare mass, or the not the free field theory mass. Yeah, the little m there, and then the big M. The big M obviously includes some, so I was off by some momentum factor in my relation for M, right? Because M is changing, so it must have some momentum dependence. I have to, unfortunately, I took these pictures from a different book than what I took my notes from. Okay, but I'm just trying to give you an idea of what this spectral density thing looks like, right? So it's a delta function at single particle states, and you have a couple delta functions at the bound states, and then the continuum takes over, which goes out forever, right? And it has some shape like that. Okay, but the main idea is that the mass term that we write down in the Lagrangian isn't necessarily the physical mass, okay? Because the loop corrections are going to make corrections to the mass parameter, okay? And we'll see that kind of explicitly.
The physical mass is different than the bare mass.
Yes. Yeah. Yeah.
From the conservation of the momentum and energy thing, it seems that it should be physical mass.
From
The boundary states are a little less than 2n squared.
I don't know. have to look. I think this picture's from Paston. So there, if you go back and look at Paston, it should be clear. But I'm pretty sure it's you might be right. It might be the physical mass.
The little rim is the bare mass, then of course the states are have less energy than 2M. So states.
Yeah. Yeah, I don't know. That's a good question. Unfortunately, I don't know the answer off the top of my head. But like I said, if you go look in Peskin, you can find this plot and a whole, 5 or 6 page discussion on this. Okay, if you're interested. What I want to do is get into the nitty gritty and compute the real corrections. Okay, so enough of this, formalism garbage. Okay, let's get into computing some loops. All right. So we're talking about the propagator. Okay, so at order g squared, we're going to have some corrections. Okay, so we obviously have the single propagator, right, the free propagator that I'm not showing, right, or I am, and you just can't see it, right? And then we have corrections. So the next order corrections are this loop, right? And then we said anytime we include loops, we have to include counterterm diagrams that correspond to those loops. Okay? All right, so what does this look like? So the exact propagator, which I'm denoting by a bold font, whether or not you can tell or not, is a sum over all these diagrams. Okay? So we would have, so this is leading order, right? The bare propagator. Here's the next to the leading order part, right? I can tell that because I have 2 propagators, right? And then I have one factor of what we call the self-energy. Okay, the self-energy is the stuff that can happen, once you strip off those propagators, right? This is at order g squared. You would have more corrections at order g fourth, and so on and so forth, okay? And like I said, the tree level propagator, we know what that is. That's the 1 over k squared minus m squared. Okay? And what we're after, though, is this thing called the self-energy. Okay? We want to compute the self-energy because that'll tell us a lot about not only the mass parameter, but it'll tell us about the renormalization of the fields themselves. Okay? So let's compute this loop. All right. So I've already applied all the rules. I've got momentum k coming in. I've got some undetermined momentum L in there, and on the top, I've got k plus L after conserving momentum. Okay, so let's use our Feynman rules, right, to write down the amplitude. Okay, so we've got what? We've got 2 vertices. Okay, I've got 2 factors of 1 over I coming from the propagators. Where is that 1/2 coming from? Symmetry property, right? So that diagram has a symmetry factor. So you have to include that, okay? And then I have 2 propagators. I have one propagator for the propagator that just has L, right? And then I have another propagator that has momentum L plus K, okay? And then I included my Feynman rule for the counter term, right? Which we wrote down at the end of class, I think last week, okay? So we can rewrite those. Remember, A and B are just, we wrote shorthand for these 2 factors. Okay. Okay. All right. So before we do that, we'll compute this guy. Okay. But before we do that, we start to notice a pattern. Okay. And what you find is that if I sum over all the diagrams, you can always reshuffle them to look like a power series, basically a series in the self-energy insertions, right? So I would have one diagram where I would have all the loop stuff going on in here. I'd have another diagram that looks like this, where I would have some loop stuff here and some loop stuff here, but they don't talk to each other, right? And then I would have one with 3 and one with 4 and one with 5 and so on and so on, right? And what you find is it takes the form of a geometric series. Okay. Do I talk about that here? No. Oops. Wait, where the hell am I? I got lost. Yeah. Okay? Yeah. All right, so what we have is basically a sum over these self-energies, these self-energy insertions, okay? And what we have, or what we're considering, are what are called one particle irreducible diagrams, or 1PI, okay? That means that inside those loops, inside these pies, right, we're only considering 1PI diagram. So this is an example of a 1PI diagram. A 1PI diagram is defined by, it has a property of, if you cut one of the propagators, if I took a pair of scissors and snipped one of them, I can still get to any point, right? It doesn't disconnect into two parts. See what I mean? So I could come here and forget about the external parts, okay? I'm talking about the internal parts. So I could snip here, I could snip there, I could snip, I could snip any of those internal propagators, and I'm always going to have a fully connected diagram, right? This is not 1PI because I can snip this internal propagator, and it's going to split into two pieces. Okay, so what happens is this guy, if I snip it, it's now 1PI, right? And all we want to do is consider 1PI because we're grouping everything into those factors of the self-energy, right? So what I'm saying is that out of the myriad of diagrams, loop diagrams that you can have, you can factor them into these 1PI pieces. So this guy is 1PI, right? So there's not a contribution in this where there's two separated loops, right? Because that would be a contribution to this guy, okay? So it determines how we compute this guy and how we write it down, right? For example, so this is an example of in 5 cube theory at order g squared. Yeah, so at order g squared, that the ones we just computed, this is the only diagrams you can write down. But as you go higher order, you got a whole slew of weird looking diagrams. You got the snowman diagram. You got the guy with weird hair. No, it's a tomato diagram. Then you got the pill diagram, and so on and so forth. Okay. All right. So those would contribute to the self energy, that blob inside of once you strip the two propagators off. Okay. And what you find is you sum these up. It's basically a geometric series. Okay. And we know how to resum or how to sum a geometric series, or maybe you don't. It's okay. But what you would find is that if you do that, you can resum it and get an expression for the total or for the exact propagator. Okay, and it looks a lot like what we had before, except you see that those blobs, right, those insertions of the blobs, get summed up, and they basically shift the mass parameter, right? So you can forget about that I epsilon, right? And what you see is that k squared doesn't have a pole anymore at m squared. Okay, so remember back when we talked about the single particle propagator, that it had a pole at m squared, and that determined how we did the integration and all that stuff, right? Well, now that's not the case. If the self energy is non-zero, then the pole is going to be shifted away, right? Or it might be a branch cut or whatever the weird stuff that you get in that type of stuff. Okay. All right. So again, m squared here would be so m squared here would be the Lagrangian mass. So that would be the bare mass. Okay. And the physical mass is going to be whatever the pole is. So it's going to have. So this is the Lagrangian mass, the bare mass, and this part, when it is included, is going to give you the physical mass. Okay. All right. Where are we? Yeah. So whatever. If you understood the Lambda-Taylor exact propagator, it kind of tells you that you're on the right track, right? So you trust those guys because they're hardcore theorists. We did it, just by summing up diagrams. and we see that we get basically the same thing, same behavior, that loop corrections are going to shift the pole from m squared to something else. Okay. All right. So what? Okay. So we have, remember, like we were saying, that the exact propagator at tree level has a pole at k squared equals m squared and has residue 1. Right. So we want the same type of behavior out of our exact propagator. Right. And the only way that can happen is if when we set k squared equal to m squared, this self-energy vanishes, right? And likewise, the derivative with respect to k, or k squared, evaluated at m squared has to vanish. Okay, and these are going to be the two conditions that are going to allow us to compute those counter terms, right? Because remember, when we compute the self-energy to next to leading order, we've got should be there. Yeah. Oh, there it is. Right. We've got this term from the counter term. Right. We've got two unknowns. Okay. So what we want to do is compute the self-energy, and then from the self-energy we can apply these conditions that will allow us to compute the counter terms. Okay. All right. And then from those we can obviously get Z phi and Zm. Okay, so now we come to the part where we have to, we've done all the nice, well, it's not really nice, but we've done all the theoretical stuff we can do. Now we have to really get down and, down and dirty and try to compute this loop, okay? And so what we have after we factor everything out is an integral that looks like this, okay? All right, so let's do a little let's do a little dimensional analysis, okay? So the numerator, this guy has mass dimension of what? No, this is a momentum. This is a momentum. So it'll have mass dimension of d, right? Okay, so that has mass dimension of d. The denominator has mass dimension of 4, right? M squared, just set the momentum to 0. It's m squared times m squared.
Right.
Okay, so we've got something that has mass dimension of d, and basically d minus 4, right? Because the minus 4 is coming from the denominator. Okay, so if we have something with mass dimension of d minus 4, all right, so what? Well, we know that this integral goes from 0 to infinity, right? So that's telling us that if d is greater than 4, or even equal to 4, then we're going to get a divergence, right? So basically, it's going to go like a factor of k. See what I mean?
Yeah.
Because we have an integral. Let me see if I can do it schematically. So we have some integral that goes like d. Let me just forget about those two pies. ddl, right? And then we have 1 over L squared minus M squared. Let's just look at. Let's just drop the mass. So we have L squared and then L plus K squared. Okay. So we've determined that this thing has mass dimension d minus 4. The mass dimension is d minus 4. Okay, so what? So if the d is equal to 4, right, then these mass dimensions are going to cancel out, right? But I still have to do this integral, right? So it's like, doing an integral d by dx of 0 to infinity, right? You're going to get an infinity, right? So if d is equal to 4 or greater, we're going to run into divergences. Okay? Make sense?
Right.
Okay. And these are the same type of ultraviolet divergences that we've encountered before. And remember there, I introduced a cutoff, right? We said one way we can deal with these things is to basically just cut off the momentum integral. Like, don't go to infinity because we know we're screwed up there. We don't know how to compute things up there. Okay, that's one way of doing it. the other way is what's called dimensional regularization, okay? Or DEMREG. Okay, I'm gonna call it DEMREG because I can't say regularization 20 times, all right? So the name of the game in this little technique is that you compute the integral in a safe region, right? So you compute it in a region where, for example, d is less than 4, okay? And then you do the integral. This little piece of information will let you do the integral, and then you can take the limit, right, as d goes to 4, or as d goes to 6, whatever, right? Because anything greater than 4 is going to give you infinities, okay? And in this way, we'll be able to extract the infinities, and those are the guys that we want to cancel with the counter terms, right? Okay, so before we introduce DEMREG, we want to use a trick that Feynman introduced. And it's basically a trick where you want to take an integral. Well, maybe I have it on the other side, but this is all in words, okay? So basically, it's a trick where you want to do an integral, or let's say, yeah, you want to rewrite. Let's say you have some factor of 1a times b. Okay? And what he said, what he noticed is that you could split this up, do it by introducing a parameter that he called the Feynman parameter. No, I don't think he called it that, but and you can rewrite this guy like this. I think this is the way it goes. Does that make, no, it doesn't make sense. Let's see if I'm getting this right. It's over. That's over. Yeah. All right. So you can rewrite this like this. Well, I'm not going to write it. It's up there. Okay. So what he noticed is that. So the name of okay. So this is the name of the game. You have some combination of denominators, right? And what you want to do is basically try to get it to where you can write this as, you use this as one single denominator. Okay, so we're going to go from something that looks like L squared plus K squared minus M squared, to L squared minus M squared. So this is the denominator we have now, right? What we want to do is we're going to use this trick and get it down to an integral that looks like this. Let me call it Q. So we're going to do a change of variables along the way, but the point is that we would get something that looks like, let's just call this omega squared, n squared. Okay, so we go from this two denominator thing to a single denominator thing, which is a lot easier to compute. Okay, so that's the name of the game when you introduce these Feynman parameters. Okay. All right, so let me make sure. Yeah, so that's what that point says. And we shift L y constant, so that's the change in variables. Right, the result is going to be spherically symmetric because it's just going to go like Q squared or K squared. But the trade-off is that when you do these tricks, you kind of, you're exchanging an integration over these two things with an integration over the Feynman parameters, okay? And those can be tricky in the end, okay? So this is what the trick looks like, all right? So you can rewrite 1 over AB by introducing an integral, right? Integrating dx from 0 to 1, okay? And rewriting the denominator like that. Or, so that's introducing one parameter. You can actually introduce two parameters and make it even simpler and include a delta function, right? So the sum, anytime you have multiple Feynman parameters, the sum of those parameters is always going to give you 1, okay? All right, so in general, you can do, like I said, you can do multi-denominators into a single denominator to an n power, okay? And so you get n denominators, single denominator to the n power. Okay? All right. And I think I'm going to put the brakes on right here because I'm running out of gas. But we'll stop there. So what we're doing is we're trying to compute this integral. Okay, we're going to use the Feynman trick to basically combine those denominators, right, into one super denominator. No, I'm just kidding. Into one denominator. That denominator is going to be spherically symmetric, so we can do the integral. The problem is we're working in d dimensions, right? So how do what does spherically symmetric mean in d dimensions? Okay, so that's the next part that we have to work out. All right. The good news is that after the next few slides, we're going to have a master formula. Okay, that'll be good for any loop diagram. Okay, so we won't have to go through these arguments every time you compute a loop. All right. Okay. All right. So I'll see you. What's today? Tuesday.
Yeah.
All right. See you Thursday.